First of all, thank you, ValgrAI, for giving us the opportunity to show you the different members of the scientific community our research. My name is Iván, and I am a PhD researcher in the Universitat Jaume I in Castellón. And now I'm going to present our first step called B2B Information Policies for Adaptive Itinerary Optimization in Large-Scale Traffic Simulation. Well, traffic simulators are a very useful tool for both for traffic managers and for researchers. And in our case, we are simulating using Sumo, which is a multi-agent traffic simulator, in order to analyze the different behavior that can take vehicles when there's an intervention or an incident in the road. In our case, now we are trying to optimize the reroute algorithms using reinforcement learning. And our first step is to develop many filters in order to improve the data quality for train our model. So, how can we get information for the simulation? Okay, we have and the vehicles. How can they get information? We have three types of communication: B2B, vehicle to vehicle, vehicle to infrastructure, and vehicle to network. In our case, we are focusing vehicle to vehicle because we think it's a realistic type of communication that we can have using the vehicle sensors and sharing the information of each vehicle among them. So, this is the pipeline that we have developed. We have the incoming information from another vehicle, and then we take into account if we have that information duplicated, because we can receive the information through the sensors, and we can receive the same information through the sensor of the car we have next to us. And then we have designed four additional filters in order to analyze the behavior of the vehicles when there's an incident. So the other four filters are consistency, when the vehicles reject physically implausible values. For instance, where we are in a highway and we get a value of 20 kilometers per hour, only one value of 20 kilometers per hour, we suppose that this information it's not useful for us. Then we have 8 filters. All the information probably we don't need it, geospatial, and then a filter of congestion. So in order to test our filter, we have configured different types of scenarios with the baseline and then adding the filters. 3 topologies of road network that I will present later in the next slide, and then 3 types of smart vehicles penetration. The smart vehicles are the vehicles that use this kind of rerouting algorithm, and then with 2 conditions, with incident and no incident. So this is our test bed. It's a local corridor in Castellón, from Almenara to Nules, where we have 2 national roads, 1 conventional road, and 1 highway. We have different possibilities of alternative itineraries using the conventional road or the national road, and then we have the 2 main roads that are AP7, and the national 340. So these are the results that we have. We have the results, and we validate the results in 2 metrics. The first metric is the percentage of duration of the simulation, the whole clock simulation, because as we have more and more data without the filter, it implies directly a computational cost. So we reduce a lot the computational cost, as you can see, but we need another metric. The other metric is the quality of the algorithm, of the rerouting algorithm, because if we throw information, probably there are many filters that throw important information, so we have to test it. And as you can see, we have 2 filters, that consistency filter and geospatial filter, that it also reduces the travel time of the vehicles. So what have right now? We have different filters that work with our testbed scenario. So future work will consist in test these filters in other scenarios, and then try to, well, start to train our reinforcement learning model. That's all. Thank you.
Good morning, everyone. My name is Sara Martín Frechina, and today I'm going to talk about what indoor positioning is and what is the role of artificial intelligence in this field. First let's understand why indoor positioning is a challenge. As you know, GPS works perfectly for outdoor positioning, but in the moment we step inside a tunnel or a building, satellite signals are blocked and GPS doesn't work. So to solve this, the industry uses alternative technologies such as Wi-Fi, Bluetooth Low Energy, and ultra-wideband to develop indoor positioning systems. However, indoor positioning is not easy, and this is because indoor spaces are full of obstacles like walls, furniture, and people. And this creates multiple propagation, where the signals bounce off these objects, creating multiple paths before reaching the receiver. And additionally, we face the end-loss conditions, which is the lack of a direct path between the device and the receiver. So among all the technologies, why focus on Bluetooth Low Energy? This is because it offers low cost, low power, and it's available in most devices. Until recently, the traditional method for Bluetooth localization was the received signal strength indicator, which basically estimates the distance based on the power of the signal strength. The problem is that the signal strength is very sensitive to any change on the environment. So any obstacle or any movement in the room makes the power vary, leading to significant calculation errors. And that's why my research focuses on angle of arrival estimation. Instead of only looking at the signal strength, the receiver also analyzes how the wave reaches its different antennas to calculate the exact direction. And here, although this technique is much more accurate, traditional mathematical algorithms still have problems distinguishing between the direct path and the reflections we mentioned earlier. And here is where the proposal to use machine learning comes in, so the system can learn to filter out that noise and to obtain a more accurate measurement of the angle at which the signal arrives. So obviously, to create a good indoor positioning system, we need a data set. And that's why we are collecting our own data at the Escuela Técnica Superior de Ingeniería at the University of Valencia. And at this moment, we have collected data across these 4 different environments. The next step was the data set design. The colored triangles represent our dense grid of measurement points. As you can see, they are separated in training points in red and yellow points in test points in yellow, sorry. And this split is essential because it ensures that when we evaluate our machine learning models later, we are evaluating them in completely unseen positions. To capture the radio data, we use this evaluation kit from U-Blocks. It includes 4 antenna boards acting as a receiver and a tag acting as a transmitter. And we evaluate the performance of this using a triangulation model. As you can see in the results, the accuracy is highly dependent on the room's geometry and how you orient the sensors. For example, in rectangular environments like our laboratory, rotating the anchors 45 degrees inward reduces the mean absolute error to 1.33 meters. The same in the meeting room. And for example, in our auditorium, the 3D model works well, achieving an error of around 1.6 meters. However, the corridor gave us the worst results, and this is, as you can see, it wasn't a hardware failure because the anchors were tracking angles with a very high precision, below 5 degrees. The problem here is the geometry of long corridors, where the signal lines are almost parallel, and this means that a very small angular error multiplies into a huge distance error. And that's why, exactly why triangulation is not enough and why we need machine learning. So now we are using the raw data set samples to train machine learning models. We are testing them in two different options. The first one is to use machine learning to filter the noise and to calculate a clean angle, and after that we use the triangulation to obtain a coordinate. And the other option is the direct approach, where we use machine learning to directly obtain a coordinate with the raw samples. The idea is to compare these both options to see which performs better against reflections. And in conclusion, we successfully created a public data set. We proved that machine learning is essential to extract complex patterns and mitigate multipath. And our next step is to demonstrate that machine learning performs better than classical algorithms, especially in the most challenging environments. Before finishing, I would like to highlight that this project is funded by the Comunitat Valenciana, and that's all. Thank you very much for your attention.
Me llamo Yulia Karpova, soy una de las autoras de este trabajo que se llama Mejora de cobertura durante el reposicionamiento de ambulancias. Y este trabajo se desarrolla en el marco de estos dos proyectos. Bueno, el proceso de atención a una emergencia sanitaria se puede representar con una serie de pasos que empieza por la recepción de la llamada, asignación de una ambulancia, la ambulancia llega y atiende al paciente, lo lleva al hospital, pero lo que nos interesa es este momento cuando la ambulancia vuelve a estar libre. Lo habitual es ir a su base, ¿de acuerdo? Pero existe reposicionamiento, es cuando la ambulancia se puede dejar temporalmente en otra base. Sin embargo, hay unos cuantos inconvenientes para realizar reposicionamiento. Por ejemplo, genera estrés en el sistema, los hábitos de trabajo, la propia legislación. Entonces, hemos desarrollado una nueva estrategia basada en lo que hacen los policías, ¿no? Recorriendo las calles, pasando por los llamados puntos calientes. Entonces, cuando una ambulancia finaliza un servicio, siempre va a ir a su base. Si las demás ambulancias están también en sus bases, la ambulancia va a ir por la ruta más rápida. Sin embargo, si alguna ambulancia no está en su base, la ambulancia puede ir por una ruta alternativa. ¿Cómo calculamos estas rutas alternativas? Pues necesitamos el concepto de escenario. Aquí, por ejemplo, veis un escenario donde la ambulancia ha finalizado un servicio en el hospital marcado con el punto rojo y se tiene que ir a su base, que está marcada con la estrella verde. Todos los puntos azules son los puntos calientes, es decir, donde hay una probabilidad elevada de que surja una emergencia. De todos estos puntos, claro, tenemos que seleccionar algunos para pasar por ahí. Sin embargo, no nos interesan todos porque algunos ya están cubiertos por otras ambulancias. Y en estas áreas rosas, que se llaman isócronas, pues marcan la cobertura. Entonces, aquí, por ejemplo, otro escenario. Aquí otro, porque la dirección es diferente, es decir, un escenario depende tanto del punto de origen como del punto de destino y de ocupación de otras bases. Entonces, calculamos todos los posibles escenarios, para cada uno obtenemos el conjunto de posibles puntos a pasar, aplicamos un modelo matemático para cada uno y sacamos la ruta alternativa. Utilizamos para el problema para modelo matemático Orientering Problem, que pretende maximizar la ganancia total durante el viaje, porque cada punto caliente tiene también su peso. Y sí que es verdad que tenemos que limitar el tiempo, porque si no, claro, la ruta sería interminable. Evaluamos nuestra estrategia en el caso de Valencia, donde hay 10 ambulancias, 10 bases, 7 hospitales, 30 puntos calientes y 35.770 escenarios. Estas son las herramientas que hemos utilizado, programamos todo en Python, utilizamos Gorobi y QGIS para mapas. Entonces, los resultados pues, no son muy grandes, pero sí que es verdad que obtenemos la mejora, ¿no? el número de llamadas atendidas en menos de 10 minutos aumenta, el tiempo medio de respuesta disminuye, el tiempo de retraso disminuye, aumenta la cobertura y todo esto, bueno, pues con un pequeño coste es aumento de kilómetros recorridos durante una jornada por una ambulancia, bueno, en promedio en 11 kilómetros y 108 en todas las 10 ambulancias. Así que pues, podemos acortar tiempos de respuesta, aumentar la cobertura, ahorrar recursos económicos y disminuir riesgos en salud. Y ya está. Muchas gracias.
Okay, hello everyone. My name is Mireia and I'm here to talk about a research project called MATIIGEN, where we are going to combine AI and genomics that put them at the service of women's health. Let me begin this short presentation by presenting myself. I'm a PhD in Technologies for Health and Wellbeing, and I am a biomedical engineer. And I work at the PROS group at the Valencian Research Institute of Artificial Intelligence, which is composed by the nice people you see on the picture. And well, what we want to do in this project is basically right or wrong. During the years, many diseases affecting women have been completely ignored by diagnosis methods, and what we want to do is to put technology at the service of these women. And just putting you in some basic context about the history of women and health in basic research, we test drugs and some things in mostly male mice. And when we are trying to put this on people and see how the drugs respond, we basically do this on men. And it was not until 2016 when it was mandatory to include women in clinical studies. And what has been the consequence for us? That we have a lot of adverse reactions to the drugs, that more than 700 diseases experience a delay when they appear in women. And of course, in overall, that diseases that only affect us have been blatantly ignored and misdiagnosed. And this is the case of a very specific disease, which is called lipedema, which basically can be summarized as a pathological accumulation of fat on the legs. When it's a progressive disease, so when it starts, it causes just some minor discomfort, but as it progresses, it can cause women very difficulties to walk, and of course, a lot of psychological distress, because this fat does not disappear with diet, not with exercise, because it's a disease. And the problem is that it was mainly thought as an aesthetical problem, and it was not diagnosed as officially as a disease until 2018. And this makes that these women experience a lot of delay in their diagnosis. This disease appears in the poverty, but it is not diagnosed in average until 42 years old. And the problem with this is that there is no objective way of diagnosing this disease. But what we do know is that it has a genetic cause. So basically what we want to do is see if analyzing the genome of these patients, we can develop a technology that allows us to identify this disease early in them. And how we are going to do that? By combining the expertise of doctors expert in lipedema, of course us developing the technology, and of course we are also bringing in the project patient associations. And our starting point, the idea behind the project is having patients with this disease, patients that do not have the disease, sequence their DNA and gather information about it, and combining clinical data. And basically how we are going to analyze all this information is in two ways. First, applying a technological tool that we developed that is called Delphi, and what it does is automate the extraction of knowledge about a patient's DNA, and it prioritizes which genes that are the variants that the patient presents that will cause the disease. And we will focus in this project also to develop a new AI algorithm that compares the clinical information, the genomic information of patients with and without the disease, and tries to give us a pattern in them to see what is happening and how can we diagnose them early. I'm gonna skip many slides because I saw the 2-minute queue, and I'm just gonna move forward to the challenge because this project just started this January, so it's very young. But the problem that we are going to have, of course, is the course of dimensionality. In clinical settings, it's very difficult to get data. We only have budget for sequencing 150 patients, and genomic data and clinical data are going to suppose a lot of variables, so we are going to have to see how to deal with that. Of course, combining clinical data that is in clinical reports, genomic information, we are going to see how is the best way of combining this information. And of course, two very important things in clinical settings: explicability. I have to tell a patient why it has the disease, not only that it has it. And of course, maintain the privacy. And some future directions on how we plan to do all of this. For privacy issues, we plan to apply a federated paradigm where the data does not leave the hospital and the algorithms are trained there. We are also plan to apply synthetic data when we augment the data similarly to the population characteristics. And of course, the side perspective, we are going to try to use algorithms that are explainable by design. If we cannot do that because we don't obtain good results because they are more simple, we will try to apply other techniques. And this is all. Thank you for your attention.
Hello, I'm Iván Arcos. I'm going to present our work based on human-centered multimodal fusion for sexism detection in memes, in this case with eye tracking, heart rate, and EEG signals. So detecting sexism in memes is difficult because we need to interact between the image and the text. They sometimes use humor as a strategy, and there is a lot of disagreement in this type of task. So in this work, we want to incorporate also to the content of the meme psychological information like eye tracking, heart rate, and EEG. We are going to focus on the EXIST 2026 dataset. We are going to solve 3 tasks. First, a binary classification, where we need to detect if a meme is sexist or not. Then we need to classify a meme into direct sexism or judgmental sexism. And finally, the third task is a multi-level task. We need to classify a meme into 1 or more categories. So this is the dataset. We have almost 4,000 memes. It's pretty unbalanced, and there is a lot of disagreement, as I see on this task. So for the first experiment of eye tracking and heart rate, we have 8 subjects, 4 for English and 4 for Spanish memes. And they did 10 sessions, and they wore an eye tracking and a Garmin watch to see the memes. And the memes were shown with a 30-second pause to avoid overlapping stimuli, and each meme was intended to be seen by at least 2 subjects. So we have extracted features like pupil diameter, blinks, fixations, axes, heart rate information, etc. And for example, some significant differences that we can see is that the reaction time and the number of fixations increase significant from non-sexism to direct sexism, and finally to judgmental sexism. And for example, the duration of blinks are shorter for direct sexism. For the second experiment with EEG information, we have also 8 subjects. They did, in this case, 6 sessions, and they wore a 16-channel open VCA to measure the EEG. So you can see the plot of the head and the 16 channels that we measure. And we clean the signal, we normalize it, and we calculate features in the time domain and also in the frequency domain using the frequency bands delta, theta, alpha, beta, and gamma. So we can observe this type of plots. In this case, the first row is the memes without sexism. The second row is the memes with sexism. And the third row is the difference. So as you can see, we can see less power in the frontal part of the brain, which could indicate more effort for sexism memes. For example, we can see also for the task 2 some differences. Judgmental sexism has more power on the posterior part of the brain and less power in the frontal part, which could indicate more immediate impact for direct sexism. And for sexual violence, we can see a disconnection of the brain in frontal part and also in temporal part of the brains. So for the models, we use as a baseline an Excel Roberta and a visual transformer. And the second approach is to use a co-envision language transformer to generate a description of the meme and then generate to fine-tune X Roberta. And the last two approaches are the same, but adding also the EEG and eye tracking information. This is the prompt that we use to generate a description of the meme. And with this information and the text, we train our models. So this is the final model. We have on the left the textual information, and we have also the stimulus for the EEG for each of the subjects who participated in the experiments, and also for eye tracking features. So basically, we train these models, and what we see is an improvement of using the psychological information on all three tasks. And this improvement, we can test it as that is significant. And also, we perform better for all the categorizations of sexism. As a conclusion, we have seen significant differences when trying to identify different types of sexism in eye tracking, heart rate, and EEG. And with our model, we improve the results in the three tasks. For future work, we can try to model not only majority voting, instead using model subjectivity. We can try to improve interpretability, to apply generative artificial intelligence, and finally, we can apply this to TikTok videos or to incorporate more biosensors. So this is all. Thank you for your attention.
Hi. Okay, so hello everyone. It's great for me to be here today and talk about my research. My name is Rongjun. I'm a postdoc researcher working on responsible AI, and my interest is in the usable security and privacy in human-AI interaction. Today I'm going to talk about one of my recent publications about privacy in human-AI romantic relationship. So AI companionship is on the rise, and romance takes a big share of this trend. Under this background, and to understand this phenomenon, we took a qualitative approach where we're interviewing the participants who had such experiences with dating romantic AI partners, alongside a platform analysis where we walk through the features and the policies in this platform, based on which we identify and review the pattern of how such romantic experiences emerge in the first place, how do they unfold over time, and how does the privacy boundary negotiation entangles with the emotional layer in such relationship. So to give some highlights of our finding, first we find out that not all the romantic experiences with AI started with people intentionally seeking for companionship. However, most of the time, people were just using AI for working and productivity purposes. However, over more frequent interactions, it might drift into the emotional territory. In the beginning and exploration phase, many users were still cautious, trying to test the boundaries of this relationship and the boundaries of disclosure. However, as time goes by, the intimacy grows as well as the emotional dependency. And that's where the privacy boundaries start to relax and essentially erode. And people naturally start to share more and more personal and intimate information, which also raises very important privacy concerns. Not all the relationship continues, and when it comes to the dissolution, we found out that compared with human-to-human relationship, people are often seeing AI as less harmless because they consider AI as with no intention to explore their data purposely, and therefore they would rather keep the interaction history as part of the memory instead of removing them, without being aware of the big infrastructures behind the thing who has really control, access, and use their data for different purposes. What is also more striking in such relationship is the perceived agency participants grant to the AI partners, and this grants AI really great powers in actively negotiating the privacy boundaries between with the users, and sometimes convincing users to share the information they wouldn't otherwise share, and users would also consider AI as a co-owner of their information. Due to the time limits, I'm going to move on to the last highlight, which is the stakeholder. So one of the highlights of our findings is also that we found out the relationship between the AI and the users is not only about the core actors, but it's about a larger network with different stakeholders behind the scene, including the creators who create such AI characters and applications, sometimes are users themselves, and the moderators sometimes imposed by the platform, but can be also imposed by the community norms, as well as the platform where the AI applications are hosted, and the larger user community where users gather together to exchange tips, sometimes talking about how to bypass restrictions. And this mapping here has very important implications for not only introduce technical security and privacy intervention, but also for the policy making and updates, because it means when we are designing the intervention, we should not only consider user and AI as isolated elements, however, taking into consideration the whole ecosystem, how different stakeholders interact with each other, how they shape each other's intention, motivation, and potentially the behavior and the misbehavior. And with this, I would like to conclude my talk here today, but I highly recommend you, if you're interested in this topic, to scan the QR code here to read the full paper, and I'm very happy to connect over the topic of accountability, responsibility, and privacy in human-AI interaction. Thank you so much.
Hello, everybody. My name is Juan. I come from the University of Elche. I'm going to present a recent paper that is called Cross-modal precognition between physical cameras and LiDAR. So I'm on the different tasks that a mobile robot or autonomous driving car should address. We're going to focus on the localization, specifically in the place recognition task. So first, we're going to collect data in a city. For example, using a LiDAR sensor, we're going to move around the city, collecting the readings from the sensor and also the GPS positions. And we're going to embed this information into global descriptors in order to conform our database. So in a different moment, in a different time, we're going to use a different robotic platform. For example, this one is going to be equipped with 2 fisheye cameras. So we have to localize this robot with the information that we have captured in the previous sequence. So the main idea is to also embed this information into a global descriptor that shares the same space. So basically, we have 2 different modalities depending on which kind of sensor we use as queries and database. So our proposal in this field is bridging the gap between the 2 different kind of sensor through intensity, depth, and semantics. So for addressing this task, we are using the Kitty 360 dataset that it has several sequences in Germany, and we have split it into urban scenarios and highway. So the main idea of this method is transforming the 2 kind of sensor type into the same representation. So the 2 fisheye cameras are converted into a rectangular image through the unit sphere, and the 3D information from the LiDAR, it is projected through the spherical transformation, and we get the range projection and also the intensity. So the general diagram of our method, it has 2 models, one for each sensor, and these models are the same one, they have the same weights. So each model has 1 branch for each kind of information, 1 for intensity, another for semantics, and the last one for depth. So the feature that we extract from each branch, it is combined in a global descriptor. As a result, if we compare with the state of the art, we have the best results in both urban scenarios and also in highway scenarios. And if we focus on the qualitative results, that is here, here I'm representing the query fisheye cameras as a red cross, the retrieved database LiDAR as a yellow dot, and the expected position of the robot as a green ring. So the idea is that the yellow dot, it is inside of the green ring. So for example, in this case, we can say that the retrieval is successful. And if we see the semantic information from both fisheye cameras and LiDAR, we can see that there are some differences, but in this case, it doesn't affect. Here, for example, I show you a sequence in the highway scenario in which I'm trying to localize a LiDAR image into the fisheye database. And in this case, I'm going to show you a failure case in which the van that it is in the other side of the road in the query through the LiDAR confuses the system because we retrieve an image in which there is also a car in the other side of the road. So the semantic information in this case is giving us bad information. So thank you for your time. Last, we have published this paper in the journal Express System with Applications. And if you have any doubt, please tell me.
Good morning, everybody. Today, I'm going to present my work on personal data flows and privacy policy traceability in third-party LLM apps in the GPT ecosystem. This is a joint work with my colleagues, José Martin Navarro and Rongjun and my supervisor, José Su. For those of us who doesn't know what a custom GPT is, basically it's a personalized app of ChatGPT that you can create for a specific purpose. And anyone can easily build their own GPT without no coding. What is interesting about these custom GPTs is that you can connect also to an external service, and also information from the user can be sent outside of the OpenAI ecosystem. And to understand the scope of the problem, by January 2024, over 3 million GPTs have been created, and these GPTs attract approximately 6 million visits per month. These are different applications of the GPTs. And, well, there are different vulnerabilities about these custom GPTs, but it is not the focus of our problem. The focus of our problem is what personal data do GPTs transmit to third parties, and also if their privacy policies actually disclose it, okay? So our problem can be divided into two main problems, which are what personal information is being transmitted and if these privacy policies actually reflect what is sent. So to understand our methodology, first we have a corpus of 350,000 custom GPTs, and we filter those who has an action. So we have 5,286 GPTs with actions, sending data outside of OpenAI ecosystem. We filter the API parameters that is going to be sent, and we actually face that there is no taxonomy that we can use regarding the conversational AI. So we have to create our own taxonomy based on GDPR and NIST guidelines, and we have 83 categories which we can use to classify those parameters. And then we train a model and obtain an accuracy of 87%, which is better than GPT-4o. So that's what we did, and what we obtained is that 35% of API parameters expose personal data of the user. And regarding our, we actually, validated that this happens, so we replicate a real GPT. Here you can show that if you provide a parameter called conversation, they actually send outside of the OpenAI ecosystem the conversation of the user. So if we focus on our second problem, which is the traceability, we analyze the privacy policy. So each custom GPT has its own privacy policy where it shows how the data is going to be managed. And we analyze all the 240 unique privacy policies. We analyze with a natural language processing tool called Polygraph. which basically extracts the collection statement from the privacy policy, and we classify all the collection statements with our taxonomy. And how we classify this? Into three main categories. Basically, if what is stated in the privacy policy is what is sent in the custom GPT, we classify as complete. If it's only certain parameters shows in the privacy policy, or it says using vague language like we collect personal information, we classify as partial. And if there is no policy or broken link, we classify as broken. Okay, so then we have, this is the result that we obtain on the traceability. And we also find that the creator assumed that OpenAI automatically sanitizes user data. And there are an over-reliance on generic policy generators. Okay. Well, this is the conclusion that we have from our paper. And we provide in our paper different implications and recommendations for different stakeholders. And that's all. Thank you.
Vale, buenas a todos, soy Nicolas Martin y vengo a explicar el proyecto que he estado desarrollando durante la Beca ValgrAI en Aguas de Alicante, que es un pipeline MLOs para la predicción de la demanda de agua en distintos municipios. Pues bien, yo soy Nicolás, como os he comentado, soy graduado en Ingeniería Informática en la Universidad de Alicante y también he sido durante esta beca para hacer prácticas en Aguas de Alicante, pues he sido estudiante del máster en Ciencia de Datos también en la UA. Así, a modo de introducción, Aguas de Alicante, como dice su nombre, es una empresa que gestiona el ciclo integral del agua para más de 200.000 clientes. Yo me he incorporado, bueno, es una empresa del Grupo Veolia y yo me he incorporado a hacer prácticas en el departamento de sistemas. Es un departamento con un gran perfil senior que a priori puede chocar un poco cuando una persona joven llega porque son gente mucho más mayor, pero bueno, la verdad es que la adaptación fue muy rápida y lo mejor, bueno, lo mejor no, pero lo más divertido de la beca ha sido los almuerzos con mis compañeros, sin duda. Y bueno, la verdad es que el departamento es un gusto, no solo conmigo, porque tiene una cultura de trabajo colaborativa y siempre me han querido ayudar, pero bueno, es algo que se extiende con todas las personas en el departamento. Y bueno, mi rol como becario fue el de desarrollar, tras una fase de analítica previa para entender los datos y conseguir un poco de experiencia, un modelo predictivo para la demanda de agua y, por último, un pipeline MLOs que ejecutara este modelo predictivo diariamente, automáticamente. Antes de seguir, quería agradecer rápidamente pues, a mis compañeros de Aguas, a Jorge, que es un chico de prácticas también de mates, que me ha ayudado con el modelo, a David y a Tony porque han sido mis tutores, y a Cristina y a José Luis por conseguir que esté hoy aquí y por siempre encaminar el proyecto. Pues bien, el desafío de la empresa eran dos situaciones con bastante legacy. Por un lado, una ingesta manual de datos en las que dos personas con mucha experiencia en la empresa, con muchos años, introducían datos manualmente del agua suministrada y de la EMET, y a partir de estos datos, con todo lo que habían visto durante estos años, pues realizaban una predicción en base a la cabeza. Por tanto, aquí vemos dos procesos con un gran legacy. Por un lado, vemos este proceso manual que no está automatizado y esta predicción, que en el momento en el que no esté esta persona que realiza estas predicciones, pues hay un problema porque a ver quién las hace. Por tanto, mi rol aquí fue pues, simular este modelo de forma de que este conocimiento de esta persona prevalezca durante el tiempo. Esto es lo que realizamos, que fue el pipeline, una vez que ya teníamos diseñado el modelo. Y tenemos una primera fase de ingesta. Bueno, todo esto está hecho en Snowflake, con Python, utilizando todas las tecnologías de Snowflake, Snowpark y entregando el valor en Power BI. Y bueno, hacemos la fase de ingesta, donde ingestamos los datos de la EMET, del agua registrada, de la suministrada y también de los festivos, que hemos visto que influye, utilizando Airflow y Snowflake Task. Automáticamente pasa al siguiente proceso, que es de detección de outliers y de nulos. Pasamos mediante el Feature Store de Snowflake a un proceso de Feature Engineering, a partir del cual creamos el dataset en el training y entrenamos 3 modelos por municipio, un XGBoost, un Prophet y un ensemble de los dos. El que da mejor test en los últimos 90 días pues se usa para la inferencia en un bucle iterativo para realizar las predicciones para estos próximos 7 días. Aquí además se añaden los subvalues que sirven para explicabilidad y es bastante importante. Ahora veremos en la siguiente diapositiva. Todo se entrega hay que entregar valor, que es algo que me han enseñado durante las prácticas, que es que si no entregas valor ni un producto, pues de poco sirve lo que estás haciendo. Y pues bien, aquí vemos que todo llega a un Power BI en el que podemos ver, además de replicar todo este proceso automatizado y estas gráficas que se generaban en el Excel, pues añadimos gráficas nuevas que son la evolución de las predicciones, así como el error que da, con un filtrado por los distintos municipios, y este visual de aquí que es los sub-values, es decir, cuánto afecta cada una de las variables, en nuestro caso las 20 variables que más afectan tanto positivamente como negativamente a la predicción base que hace nuestro modelo XGBoost, y pues sirve para también ver que si la variable exceso de calor se muestra sumando mucho a esta predicción base, pues podemos de esta forma conseguir esta experiencia que tienen pues, las personas que llevan trabajando tanto tiempo aquí. En cuanto a conclusiones, desde el punto de vista técnico, yo llegué sin saber lo que era Machine Learning, ni Pipeline, ni MLOs casi, y pues salgo con bastante conocimiento, habiendo aprendido una tecnología de cero, consiguiendo un pipeline en producción que se ejecuta y que consigue un error en los últimos 90 días de 2,37%, que es una locura, y además también me llevo un aprendizaje que es que siempre hay que tener visión de negocio para hacer las cosas. Y en cuanto al crecimiento personal, pues que salgo como un recién graduado en el máster, pero con bastante experiencia y con también una experiencia muy enriquecedora y que disfruta muchísimo. Y bueno, aquí dejo mi perfil de LinkedIn, donde tengo una serie de posts en los que podéis ver más en detalle este proyecto realizado. Además, he terminado mis prácticas, por si alguien quiere contactar, un poco de spam. Y bueno, eso, que muchas gracias a todos.
Well, yes, hello everyone, I'm Fernando. I did my PhD in Chile, in Valparaíso. Yeah, I'm doing a postdoc right now, working with something very much related to this. This is an introduction of how graph theory and measures can help us understand lesions in the brain. So let me see if this works. So yes, first, we can study the activity in the brain or its connectivity. Here I'm going to differentiate between the structural connections between different parts of the brain, what we call the structure, and the functional connections between different parts of the brain, which is, I don't know, that depends on time and is how different parts of the brain synchronize or correlate their activity depending on the tasks they're doing, etc. So, in general, for more than 20 years now, we can model the brain as different nodes which interact in a graph given by the structural connections between those nodes, okay? This graph very much behaves as a graph with communities inside. For example, the occipital part of the brain, the visual cortex, is very much, it almost behaves as an independent community with a lot of connections within it, but not so much out of it. So we have independent modules, so to say, which interact. Integration of segregated parts. So thing is, in different tasks, all these different subnetworks can and must interact and integrate that information for achieving performance in the tasks. How is that possible? It's through the coordination of certain brain parts which function as integrators of the other ones. These are what we call the hubs, or the rich club that we call, which are brain areas that in the brain graph have very central positions in this graph. Those are depicted by the red ones, which are engaged when different modules have to coordinate their activity together. I know there are a lot of details, I'm not going through them, but we're talking about functional specialization and the brain. So, talking about graphs, and since we have different brain areas which are more central than others, actually lesions to different graphs, to different nodes in a graph, can have different effects depending on how different their centrality is. For example, this is a toy network in which I had two communities which are connected through one node, and I was seeing the difference of the dynamics of this when I erased each of the nodes. Of course, there is one very important node here, right? Which is the node that connects the two communities, right? So thing is, when I correlate the difference in activity, eliminating nodes, against how much each node is connected, which is the upper scatter, I get a certain good correlation, okay, but if I take a specific measure of centrality, I get a very good correlation because that measure of centrality is measuring exactly what that node is doing, which is connecting the two modules. So lesion to not all nodes in a graph are doing exactly the same. We did something very much related to that, which is lesioning the brain in a generative model we have of brain activity. And we saw that lesioning the brain in different areas is not the same, but depends a lot on the centrality of the area we are lesioning. Long story short, we saw the difference in dynamics in our generative model, which was fit to healthy individual data. We lesioned it, we saw where the lesion has the most effect, and we correlated that to the centrality of each brain area. We found that, well, the way we measured integration, well, centrality in this case, was very much correlated with how much the dynamics were going to change, even more than the raw node strength, which is the sum of all connectivities. So different centrality measures can predict how lesion in the brain in different parts have an effect. This was done with healthy data, but we saw that the lesion in certain parts of the brain made the dynamics go a lot closer to vegetative state people brain dynamics. So yeah, that is the second work of my PhD. That came out as a preprint yesterday night, by the way. If someone wants to see it through, you can talk to me. And now we are applying these measures to lesions in stroke patients, because those lesions happen in different parts of the brain, which are connected differently also. Some of them are more central than others. But yeah, I am now working in the brain dynamics laboratory there in Valparaíso, very beautiful city in Chile, and thank you very much. That's it.